Hello everyone. We're going to be talking about in this lab tutorial is something that you'll be making tons of, which are solutions. No matter where you'll be working, you'll have to prepare or use lots of these solutions. Solutions that could be like buffers or it could be growth media for cells and stuff like that. So different type of solution that you'll be making. So we'll talk about in this tutorial. First of all, we'll define what solutions are. What are the common properties of solutions? Then we'll talk about the different types, how they can be grouped based on the size of the solute and so on. And then we'll talk about concentrations. So how is the amount of solute per unit of solution defined? There are different ways to do that, so we'll go through all the different ways. And then we'll go through some example of calculations. So how, based on the concentration that you're given, how can you calculate a mass that you need to make a solution? And finally, we'll go through a very quick overview of how you would prepare a solution if you were in a lab. So definition of solutions. So solutions are any homogeneous and stress homogeneous. I'll explain you in a second what we mean by homogeneous, but it's any homogeneous mixture of two or more substances that do not react with each other. Okay, and one of these substances is the one that gets dissolved, is referred to as the solute, and there is a substance instead, the other substance that dissolves the solute, and that's referred to as the solvent. For example, if you put some sugar in some water, sugar will be the solute, and water will be the solvent. There. Now, I stress on homogeneous. And what do we mean by homogeneous? What we mean is that if you take a solution and you take different parts of the solution, say you take a little aliquot here with a micropipette that now you should be familiar with, and another aliquot here, still same micropipette, so all different samples from different parts, they should all have exactly the same concentration. Okay, that's what we mean by homogeneous. Two substances, the solute and the solvent, are well dissolved all throughout the solution. Now, not all substances will form a solution. So in order to form a solution, two substances need to be miscible. For example, if you use salt and water, you can actually put them together and the salt will be dissolved through the formation of hydration spheres by water. Other compounds, such as hydrophobic and hydrophilic compounds, do not form, referred to as immiscible. So an example that we have here, a classical example that we always use, is oil mixed with vinegar. Mix it together, vinegar will be an aqueous solution. Mix it together, the two substances will stay separate. In this case, the oil will stay up and the vinegar will stay on the bottom part there. So they do not mix, they're immiscible, they could not form a solution. Now, solutions can be divided into different types based on the size of the particle of the solute ultimately that gets resuspended in the solvent. Now, if you're working with a very small solute, it's basically as big as maximum 1 nanometer. It's really, really small nanometer. It's 10 to the minus 9 meters, or 10 to the minus 6 millimeters. That's as small as it is. So in this case, we will refer to that solution as a true solution. If instead the size of the solute is a bit bigger, between 1 and 200 nanometers, talking about protein size, just to give you an idea, now you start talking about colloidal solutions. And if instead the particles that you're resuspending are larger than 200 nanometers, at that point you will talk about a suspension. This is not just in theory, but also they have also different appearances, the type of solution. So if you're looking at a true solution like the one here on the top, usually the solute is so small that it's unable to successfully block all light going through. And therefore, you can still see through the solution. Instead, when you look at colloidal solution, these particles start being large enough that they can start block most of the light, if not all of the light. And therefore, you cannot really see through this solution. For example, this is a glass of milk, very rich in proteins, and you can see this is actually blocking the light from going through. Now, even though these particles are big enough, they don't precipitate. differently from suspensions. In this case, you're talking about particles fairly large, quite large. You're talking about cell at this point as well. So over 200 nanometers. At that point, these particles are so big that they can block the light. Not only that, if you leave this type of solution on a bench, this large particle actually will tend to precipitate in the solvent. Therefore, they need to be mixed constantly. One example you can see here is if you take a blood sample and you leave it on the bench, you will see that over time the cells, which will be in this case the solute of that solution, this suspension, would actually precipitate over time down. And then you will see a separation from the cells and the plasma, the serum contained in the blood. Now, going to the other important point, concentration. Now, concentrations are values expressed in different units that always give information about the amount of solute that you have per unit of solution. And these can be expressed in different type of units. So there are ultimately three basic ways in which the concentration, so the amount of solute again per unit of solution, and a stress unit of solution, not solvent. So it would include solution, both the solvent and the solute. So it can be expressed in three main ways. Okay, and all the variables that you find out there, they all belong to one of these three ways. So they can be expressed as weight over weight, so weight of solute per unit weight of solution. Could be, for example, grams per kilo of solution. This is the most accurate way to express it. The reason being that, physically speaking, mass is not affected by temperature and pressure or as much as a liquid is. The second type, which you can express concentration, is weight over volume. So this will be the weight of the solute per unit volume of solution. It could be grams of solute per liter of solution. Okay, it could be different ways. Molarity is a variation of weight over volume, expression of solution, of concentration, and where the mass, instead of being expressed in grams, is expressed in moles, which is still a way of measuring mass. Finally, the last way is the least accurate, is expressed as volume over volume. And this is usually used when you have a solute that is in the liquid form, such as, for example, ethanol. You're suspending ethanol in water. Ethanol will be the solute. It's in a liquid form, so the concentration will be expressed as volume over volume. So everything you found out there can be brought into one of these three different groups here. Now, the most common ways of expressing concentration is in percentage or in molarity. Molarity is the most common one you find in the lab. But percentage is a very common way to express it. So what does percentage mean? Now, no matter, depends on what it refers to. Percentage weight over weight, there are brackets here which are missing. Percentage weight over weight, or percentage weight over volume, percentage volume over volume. No matter what, they all refer to 100 parts of solution. Okay, so it's part of solute in mass or volume per parts of solution, per 100 parts of solution. Okay, 100 parts, that can be 100 grams or 100 milliliters. So when it comes to percentage weight over weight, this gives information about how many grams of solute you need per 100 grams of solution. That's what it means. 3% weight over weight will mean 3 grams of solute per 300 grams of solution, per 100 grams, sorry, of solution. Instead of its percentage weight over weight, it means grams of solute per 100 milliliters of solution. In this case, part of solution are expressed in milliliters. Same thing when it comes to percentage volume over volume. Part of solution are expressed as 100 milliliters of solution, but part of solute are referred to as milliliter of solute. So if you have a 7% volume over volume solution, what it would mean is 7 milliliters of solute per 100 milliliter of solution. This is a very direct way to express concentration so that they're quick, solutions are quick to make. So if I tell you right away, okay, so make a solution that is 3% weight over volume, right? Make a liter of that. You very quickly, you know, it's 3%, so it's 3 grams per 100 milliliters. You already know that to make a liter, you need 30 grams. So all you have to do without thinking about the molar mass and so on, all you have to do is go to the balance and measure 30 grams of solute. It's very quick to do, unlike molarity. Molarity is the other way of expressing, very common, the most common way to express concentration. It's related, as I said before, to the weight over volume expression of concentration. In this case, molarity corresponds to the number of moles of solute, which correspond to a mass of solute, expressed in moles, per 1 liter of solution. Okay, so if you see a 2 molar solution, it means you will need 2 moles of that solute per 1 liter of solution. Okay, and then the grams, so the moles and grams can be converted into each other. You will see some calculation using what is called the formal weight or molar mass, depending whether it's a salt or a compound of solute. Okay. Let's go through some example of calculation. So when you have to prepare a solution, you'll be given a concentration, and based on that, you can calculate. The very first step you gotta do is always calculate what mass would you need of solute to prepare that solution. So depending on the way the concentration is expressed, you would do the calculations in a different way. So for example here, what mass do you need? Let's say you gotta prepare a 20-gram solution at a concentration of 2% weight over weight of potassium chloride, for example. This would apply to anything. So taking a pen here so I can highlight what I'm saying. You always start, whenever you gotta do the calculation, always start from the definition. What does percentage weight over weight means? Now, we just defined that percentage weight over weight means grams of solute per 100 grams of solutions. So what 2% means then, weight over weight, means 2 grams of solute per 100 grams of solution. Okay. So if you had to prepare, practically speaking, if you had to prepare 100 grams of solution, you would need 2 grams of solute. In this case, however, you don't have to prepare 100 grams, you have to prepare 20 grams. So how do you change the mass of solute based on that? Well, you can do that by basically using the ratio that you get there. So writing down reasonings. What I'm doing here, and one thing I want to stress in this tutorial, but also in the next one about dilution and so on, try to write down reasoning. Don't memorize formulas. Write down your reasoning. And that's what this is. This equivalency here that I wrote down is my reasoning. And what is the reasoning here? I know that if I have to prepare 100 grams, I will need 2 grams of solute. So how many grams would I need if I had to prepare 20 grams instead? Right? So that's reasoning. And the reasoning is based on the fact that no matter what is the overall mass of solution that you're preparing, so 100 grams or 20 grams, the ratio between the mass of the solute and the mass of solution should always be the same. So if it was 10 grams, the ratio should always be the same, the mass, right? So if you need 2 grams per 100 grams, how many grams would you need of solute per 20 grams? So if you resolve now this one variable equation there, you will see that based on this calculation, you find out that you will need 0.4 grams of solute, which makes sense. 20 grams are 1/5 of 100 grams. So 0.4 grams are 1/5 of 2 grams, which is okay. So now the same reasoning applies to the other percentages, but let's go through the other example. So moving on here, if the computer let me do that, there we go. So second example, percentage weight over volume. Assume that give you to prepare 25 milliliter of 5% weight over volume solution, whatever compound you need. What mass would you need of solute based on this? Well, again, you always start from the definition. So what is the definition here? It's 5% weight over volume means 5 grams of solute for each 100 milliliter of solution that you're preparing, right? So in this case, again, you're not preparing 100 milliliters, but you're preparing 25 milliliters. So how do you adjust the mass of solute based on that? You do the same thing you did before, same reasoning. If you need 5 grams per 100 milliliters, how many grams would you need per 25 milliliters? You will resolve that, and you will see that you will need 1.25 grams of solute, which makes sense. 25 milliliters are 1/4 of the total of the volume of 100 milliliters. So you will need 1/4 of 5 grams, right? Which is another way to do it. You can do it whatever way you want. Okay, here I'm trying to give you some example of how you can do the calculations. I love going through the definition first. You can do whatever way you want that suits you better. Doesn't matter as long as you give the right answer. Another thing I want to stress in all of these, make sure that whenever you do your calculation, you always keep all the units. So milliliters, grams, and so on throughout all the calculations. So in the end, you end up with correct unit. I always get students giving me masses of solute in milliliters, which makes no sense, right? And usually that counts for the fact that they don't track the units throughout the calculations. So other example now of, again, if my computer allows me to do that, is still percentage, same reason. Go through multiple times. Hopefully this will reinforce your learning there. So now imagine that your concentration in this case is given in percentage, volume over volume. And so you're asked to prepare, in this case, a 45 milliliter solution of ethanol, which is a liquid compound. And therefore, concentration is expressed as volume over volume in percentage, so of 6% volume over volume of ethanol. So what volume of ethanol would you have to transfer to make this solution? Again, we'll start from the definition. 6% volume over volume means 6 milliliters of solute, so of ethanol, for each 100 milliliters of solution that you're going to prepare. Again, you don't need to prepare 100 milliliters, but 45 milliliters. So how much would you need? Same reasoning. If you need 6 milliliters, prepare in this case 100 milliliters of solution, how many milliliters of ethanol would you need to prepare 45 milliliters? Resolve this, and you'll come out with 2.7 milliliters of ethanol. That's what you would take, and you would transfer to prepare the 45 milliliters of solution. Last couple of calculations we're doing here is regarding molarity. Okay, again, the most common way of expressing solution. In this case, the calculation requires some extra step. Okay, just because molarity, moles are not something that you can easily measure on a balance. You can measure grams. So when you do your calculation with molarity, always end up in moles of solid that you need. But then the last step you need to do is to convert moles that you came out with into mass. Simple additional step. Okay, so let's go through this example here. Imagine you're asked to prepare 150 milliliters of a 0.6 molar solution of sodium chloride. It has a formula weight of 58.44 grams per mole. Now notice I don't use the word molar mass. In this case, I use the word formula weight because this is a salt. When you put in solution the sodium and the chloride will separate right away, so they don't stay together. Molar mass will refer to a molecule that does not separate as a molecule. The elements do not separate when they are in solution. It basically is the same thing. So how do you solve this? Well, again, you start from the definition. What does 0.6 molar means? 0.6 molar means that you will need, if you have to prepare 1 liter of solution, you will need 0.6 moles of sodium chloride. So now, what do you need in this case? You don't have to prepare 150, you don't have to prepare a liter, but you have to prepare 150 milliliters. So now the first step, though, in order to do this calculation, you're gonna convert these units into the same units. So either liters into milliliters or milliliters into liters. I am converting, in this case, milliliters into liters. Okay, but you could have done it the other way around. The results would have been the same. So now we know that 150, so 1 milliliter is equal to 10 to the minus 3 liters. Okay, there is a separate tutorial on conversion factors that I'm posting with this one. So for that one, you know exactly how milliliters relates to liters, or milligrams to grams, and so on, micrograms and so on. So if I know this, now all I have to do is multiply the original volume, 150 milliliters, by this conversion factor here. It tells me exactly this, that for 1 liter, I have 1,000 milliliters. So it's 10 to the minus 3 liters. By doing that, just by multiplying there, I get that 50 milliliters now can be expressed as 0.150 liters, which now can be compared to that liter there. Once I'm done with that, so now I have everything on the same units, what I'm going to do now, I'm going to do the same reason I've done before. Based on the definition here of 0.6 mole, I know that if I have to prepare 1 liter, I will need 0.6 moles of sodium chloride. So how much would I need if, instead of preparing 1 liter, I would prepare 0.10 liters, which again should give me the same ratio between moles and volume. So if I resolve that, now it will come out that I would need 0.09 moles to prepare 150 milliliters, or 0.150 liters of solution. Great. Now, moles are great. However, they're hard to measure in a balance. Some balances do allow you to enter the formula weight or the molar mass and measure things in mole. The vast majority of them do not. Okay, like the one we have at our school do not allow you to measure masses in moles. So what you have to do then, the next step, is convert the moles into grams, which is what you can measure with our balances. How do you do that? Well, you have a conversion factor here, which is the formula weight. It tells you exactly how much 1 mole of this compound would weigh. So again, same thing, write down reasoning. Now, you have a formula there that tells you how much 1 mole will measure. So 1 mole will measure 58.44 grams. So 1 mass, expressed here in white, will correspond not to 1 mole, but 2.09 moles. The ratio should give the same, right? Resolve this, and you can figure it out by multiplying the moles by the molar mass, or formula weight in this case. You can figure out the mass corresponding to the 0.09 moles, which are 5.2596 grams of sodium chloride. This is what you will go measure on the balance in the lab, and then you would transfer it to the solution, to the solvent, to prepare your solution. Okay. Now, we say before that molar mass relates to weight over volume. So it can easily be converted into weight over volume. Sometimes it's very helpful. Again, personally, I like it better to reason in percentage weight over volume. It's more direct when I need to make solutions. So how do you convert molarity into weight over volume? And so going back, say, to this example, so how does 0.6 molar convert to percentage weight over volume? So the next time you can do your things faster, your solution faster. Again, starting from the definitions here, there are 2 definitions. So one which relates to molarity, one that relates to percentage weight over volume. So molarity means moles per liter here, whereas percentage over volume means grams per milliliter. This already makes you understand what you gotta do to get to percentage weight over volume. You have to convert moles into grams and liters into 1 liter into 100 milliliters. So how do you do that? Well, first thing is you use the formula weight, right? That already tells you what is the mass of 1 mole. The formula weight from the previous slide tells me that 1 mole of sodium chloride corresponds to 58.44 grams. Now, if I know that, well, one mass would correspond to 0.6 moles of sodium chloride. And so we already, so these, if you do your calculations here, would turn out to be 35.064 grams of sodium chloride corresponding to 0.6 moles, which makes sense. It's 6/10 of 1 mole, right? So that's the mass that corresponds to 0.6 mole of sodium chloride. So you have already converted, if you want, into mass. But now, these will correspond to the mass that you need for 1 liter. But in this case, the percentage is mass per 100 milliliters. And based on the conversion factor that we used before, we have 1,000 milliliters per liter. Now you can actually adjust this. So first you convert the liters into milliliters by multiplying. So you would have 35.064 grams per 1 liter, corresponding to 0.6 moles per 1 liter. Now you can figure out how many you get in per milliliter. It will be 35.64 grams per 1,000 milliliters. Is exactly the same thing, just converting liters into milliliters. But the percentage here refers to 100 milliliters. So this value here would have to divide it by 10, be adjusted to the definition of percentage over percentage weight over volume, which is exactly this. So the final answer will be 3.5064% weight over volume. Now, let's finish this lecture talking about how you practically prepare a solution. It's very hard to talk in theory how you prepare a solution. It's much easier to show you a lab, and hopefully you'll do it soon there. So most important thing to remind you is solution implied accuracy. So in every step, you have to try to do that step with the highest accuracy possible. So by choosing the appropriate equipment, the appropriate balance, and so on. So what are the steps in preparing a solution? Well, the first thing you would have to do is calculate the amount of solute that you need, right? And it all depends on the definition that you have, concentration so you have to achieve ultimately, and the volume of solution you gotta prepare. For example, if you have to prepare 25 milliliters of a 2% weight over volume solution, now you will need 0.5 grams. Okay, that's what. This is independent from what you're measuring, but the molecule itself. Percentage weight over volume is basically independent from the molar mass. So once you're done with that, now you're ready, operational. So first thing you do, take your chemical, you go to the balance, and you measure the mass that you have calculated. Also, you gotta use the most appropriate balance. In this case, it's a small mass, less than 1 gram. Absolutely, you would need to use what? Think for a second. Yes, you will need the analytical balance. Great, so you will measure it, in this case on the analytical balance, and then you would transfer this mass immediately, right there, beside the balance, to the appropriate glassware. What glassware would you use to measure 25 milliliters? What would be the ideal one? Think for a second. Well, if possible, if it's available, again, there are 3 criteria, do you remember, that you can. The task, in this case, requires a lot of accuracy, and the availability, and the total volume. So if it's available, what you want to go is for the glassware that has less accuracy, so a volumetric flask, with a total volume identical to what you want to measure. So because volumetric flask can only measure 1 volume. So you will look for a 25 milliliter volumetric flask in this case. And you would transfer this mass immediately inside that, right after you're done measuring on the balance. So right beside the balance, because you don't want to lose any mass on the way from your bench. So you would do it directly there. Once you're done with that, then you would take your volumetric flask with the solid inside to your bench. At this point, you can do that. And then you would add the solvent there to reach 25 milliliters, sorry, total. Now, as you can see, you add the solvent after you have the solute in there. Because if you deliver 25 milliliters in that point, the total volume will be the 25 milliliters of solvent plus the volume that is taken by the 0.5 grams right here. So your volume will be higher than the 25 milliliters. Instead, if you add the solvent, the solute already there, then you bring it just to 25 milliliters, you got the correct volume in there. And now you have to do it in two steps. First, you get to about 70, 80, 90% of the total volume. You wouldn't go straight to the 25 milliliters mark. The reason is that you want to be extremely careful you don't go past the mark. If you go past the mark, it means you have more than 25 milliliters, you would have to redo the solution. Because if instead you remove the excessive volume that you added, it's possible that some solute will be in that part that you remove. Your final concentration will be lower than what you are trying to achieve. Again, accuracy is a must in this case. So you will first bring it to about 80, 90%, and then you would take up a stir pipette and you go drop by drop until you reach exactly 25 milliliters. And then you will mix it to make, obviously it has to be a homogeneous solution mixture. Again, this exactly shows you the same thing. Sometimes it's easier to show in pictures than words. So first thing, you would do your calculation. And based on your calculation, you figure out what mass you will measure. In our case, it was 0.5 grams, so you would use an analytical balance like this one with 4 decimals there. Once you have it, you immediately transfer it inside the volumetric flask. In this case, this will be a 25 milliliter volumetric flask based on the example we did before. It has a mark here which tells you exactly where 25 milliliters are. And then you add the solvent inside the volumetric flask, but you don't go all the way to the mark, but you stay lower than the mark first. And then you finish it up using a Pasteur pipette. Drop by drop, you bring this up. So you have more control if you do drop by drop to reach the mark there, the bottom of the meniscus, reaching the line there. Finally, once you're done with that, you put a cap on top of that. In reality, here in this picture is already there, but you would add it, and then you shake it nicely, mix it, and your solution will be ready. Okay, in every step, again, you would have tried to achieve the maximum accuracy possible. Use a very accurate analytical balance. Here too, you would have brought the volume, you would have used the best piece of glassware possible to make solution, and you would have tried to reach the maximum volume as accurately as possible, going very slow, drop by drop in the solution. So finally, summary of this talk here. So what we talked about are solutions. Okay, we first define what they are, and they are homogeneous mixtures of two compounds, two substances, a solute and a solvent, which are miscible with each other. And we define the different types based on the size of the solute. If it's more than 1 nanometer, you would talk about true solution. If it's between 1 and 200 nanometers, you would talk about a colloidal solute. If it's bigger than 200 nanometers, you would talk about a suspension. And then we focus mostly on the definition of concentration, which no matter what way it is represented, it's referred to the amount of solute, whether it's in grams or volume, per unit of solution, which could be mass or volume. And then we talked about the different type of concentration. And we focus on the 4 most common ways that they are defined, which is percentage, weight over weight, which means percentage, so grams of solute per 100 grams of solution. And we talk about percentage weight over volume, which means grams of solute per 100 milliliters in this case of solution. And then percentage weight over weight, volume over volume, which means meter of solute per 100 milliliter of solution. And finally, we talked about molarity, which is defined as the moles of solute per 1 liter of solution. And then we saw how we went through some sample calculation to show you how based on the way the concentration is expressed and the total volume or mass solution that you have to prepare, how can you calculate the amount of solute that you need to prepare a certain solution? Something that is extremely helpful when it comes to prepare a solution. And finally, we went through a quick overview of how would you prepare a solution with the highest accuracy possible. And hopefully you will practice soon in a lab.